fraction, move it to the denominator. Now it's a positive 5 halves. So that would be the first thing. What else do we do, Hunter?
You can rewrite it as square root of 85.
Yeah, so we have the square root of 81 and then to the 5th power. And the square root of 81 is? 9. And I don't know, do I have 9 to the 5th power on there? No. Anybody know what 9,049?
59,049.
Oh, 59,049. You can jot that one down if you want to. 59,049. Thanks, Odette. You could definitely do a little scratch work as well. So 9 squared is 81, another 9 squared is 81. Multiply those together and then multiply by another 9. But 9 to the 5th, 59,049. So that would be just simplifying a rational exponent. So you have a value that's a fraction for a power and simplifying that power by rewriting it as a rational. So the second one, we have a little mix here. We have some rational exponents and whole number exponents. There's a little 3 on the outside. Melanie, what do you do when there's a 3 on the outside with parentheses?
You have to distribute it to every number.
Yeah, it gets distributed to every single piece that's inside the parentheses. So it's going to the 2/3, the 3, but then also the 2 gets it as an exponent as well. So every single value has to be affected by that power of 3 on the top, and then also it has to go to all the pieces of the bottom as well. So whatever's in parentheses, that 3 needs to affect each piece. So it would be 2 cubed. Melanie, it was x cubed, and then we're distributing that 3 through, so it becomes x to the 9th. The y to the 2/3, multiplying that by 3, so that would be 6/3, which is, what's 6 divided by 3? Yeah, 2. So on the top, we have 2 cubed, x to the 9th, and then you're taking 2/3 times 3. If you need to make it 3 over 1 to kind of multiply those fractions together. But 2 times 3 is 6, divided by 3 becomes 2. And then on the bottom, we're taking 5/3 times 3. Melanie, do you know what the power of x would be on the bottom? 5. Good. How about the power of the y? And then z? Good. So the 3 gets distributed through. After you distribute it through, then you have to simplify all the exponents. And when you're simplifying them, when you have fraction on the top or something on the top of the fraction, something on the bottom, you're subtracting them. So the 2 becomes an 8, and the x would be now to the 4th. Is there anything else on the top of this fraction? No. So on the bottom, we have the y's. Well, the larger power for the y is in the denominator, so that means it should remain in the denominator. And then there's a z cubed. It has nothing to combine with. It's on the bottom of the fraction. It remains on the bottom of the fraction. So we have 8x to the 4th, and then y to the 9th is z cubed in the denominator. Questions?
What about like the y squared?
Yeah, I subtracted in my head, but not actually wrote it down. Thank you. Other questions? All right, so if you look at the next one, this is an addition problem. How can we add things together? What has to happen in order for us to add terms together? They have to have the same denominator, or they just have to be the same. So they have to have the same variable, they have to have the same exponent. But in order for us to add things together, whatever's inside here must be exactly the same. So you have to have like terms in order to add things together. In front of this second parenthesis is really a 1. There's a 1 sitting there. So just like the previous problem, things are inside parentheses. There is an exponent on the outside. So we'll distribute that exponent through. So Emma, when you distribute the 1/10 through the first parenthesis, what do you get there? So x to the 4/5, because you're taking 8 times 1/10, y to the 2/5, and there's a 1 in front of there. Again, you're taking 1/10 times 4, so 4 times 1/10. And then Emma, on the other side, there's a 3, and then x to the 1/5 times 4 is, and then 4 times 1/10 is, right, y to the 2/5. So you're taking the outside power, distributing it through, and then once you distribute it through, it says to add. Well, these are like terms. They have the same variable with the same exponent. So you're adding the coefficients and just the coefficients. You don't add the powers. There's not a property that says adding. You have to do something with the powers. There's a property about multiplying but not adding. So like terms, you add the numbers in front, and pretty much the part that's the same just tags along for the ride. If that was 1x plus 3x, we would make it 4x. It's no different. So 2 other problems underneath, still working with exponents here, but these are in radical form. So we have 2 and then the square root of 9 to the 5th plus 7, the square root of 9 to the 5th, and then you're dividing that by the square root of 9 to the 7th. So Garrett, what do you think you'd do first here?
Add and top.
Yeah, you can add the top. Again, they're like terms. The square root part is exactly the same. So if we add the top, we get 9, square root of 9 to the 5th. And you're still dividing that by the square root of 9 to the 7th. So there's a plus sign. Let's add the top together. What else can you do with this problem? Lots of 9s. Melanie? So what do you mean? So because it's not equal to anything, it's not an equation, we can't square the whole thing. If it was an equation we were trying to solve, then yes. But because it's not an equation, we can't just add a square to the problem. We want to try and like simplify based off of what's up here. Connor, what do you think?
You can rewrite those square root functions as fractions.
Yeah, so these square roots we can try and write as fractions like the previous problem, so that maybe we can try and combine them together. So we still have a 9 on the outside, and then Connor, the square root of 9 to the 5th becomes,
5 halves.
yeah, so that's 9 to the 5 halves. And I'm writing a little time symbol in the middle there because it's really 9 times the square root. So when you're rewriting it, it's still 9 times that value. And then Connor on the bottom, the square root of 9 to the 7th would become 9 to the 7 halves. Okay, so now we have it written a little differently. It's written as a fractional exponent. What else can we do? Connor, what did that do to help with the problem?
You can subtract the exponents now.
So these 9s right here, they both have fractional exponents, and he said, bless you. You can subtract them. Connor, where's the larger power? In the denominator. So the larger power's in the denominator. This 9 is going to stay up on the top. We're subtracting these, but this one's going to go on the bottom because the larger power is on the bottom. So Connor, we have 7 halves minus 5 halves, which makes
2 halves, which is turned into 1.
right. So when you subtract these, 7 halves minus 5 halves, that makes 2 halves, which is just a 1. What's it simplify down to? just 1. Because now you have a 9 technically to the first on the top, but a 9 on the bottom. And 9 divided by 9 is just 1. So that whole problem goes down all the way to be 1. And then the last one up here with these exponents. We have 6 and then the square root of x squared times the square root of x squared divided by 81, the square root of x to the 16. Maggie, what do you think you could do here? So what would that do? Okay. Let's, what if we look at these pieces here? What does the square root of x squared become? X. So on the top, we have the square root of x squared, which is x. The square root of x squared, again, is also x. Okay, so on the top, we have 6 times x, which is really 6x squared. Just taking the square root of x squared, that just makes x. And then on the bottom, we have the square root of x to the 16th, which based off of what Connor did on the other side, we could rewrite that as x to the 16 over 2. That's what that really means. As a radical, it can be converted to a fraction. So Maggie, what would x to the 16 over 2 become? What is 16 over 2? 8, yeah. So simplifying those square roots by thinking about them as fractions. So the power is 16, a square root is dividing by 2, so the square root of x to the 16th is really x to the 16 halves, or just x to the 8. So Maggie, what could we do with the x's? And the bigger power is on the bottom, so that would become x to the 6th. And then what do you do with the numbers of 6 and 81? There's still a 6 and an 81. Odette, what do we do with
You
those?
just simplify them like any other fraction.
Right. So they're just numbers. They don't apply with the properties of exponents. You're dividing 6 by 81. They get simplified, as she said, like any other fraction. Odette, what is goes into 6 and 81? 3. So this would become 3 and 27. Nice job. Any questions?
Would the top be 2? The 6 times 2?
Sure. Why would it be 3? Sorry. Alright, so the last question I have on there is a little bit work with inverses, which was section 6.4. And the directions say that show f of x and g of x are inverses of each other. So it gives you two functions, and we want to show that these functions are inverses of each other. How do you go about showing functions are inverses of each other? So what can we do to determine if these two functions that they're giving us are inverses? Michelle? So he said do f of g of x, and what are they supposed to equal if you do that? X. So if you already have two functions, the way we show they're inverses of each other is to take the composite of those two functions. So Kushal, what would that look like for f of g of x?
3 times x plus 1 over 3 minus 1.
Good job. So you're taking the g of x function, which is x plus 1 over 3, and you're plugging that in for the x in the f function. So we have 3 times x. This is now x. And then there's still the minus 1. So Kushal, how would this simplify?
X plus 1 minus 1.
Yeah. So the 3's cancel because you're multiplying by 3 but dividing by 3. So that means they go away. And that just leaves us with x plus 1. And then the minus 1, which is just x. But in order for them to be inverses, you also have to flip it and do it the other way as well. So it has to work both ways. So we have f of g of x. We need to also make sure it works for g of f of x. So this is showing that two functions are inverses of each other. It's not finding an inverse. You have the two functions. We want to show that they are inverses of each other. So working the other way, the f function is 3x minus 1. You're plugging that into x in the g function. So those are called composite functions. So it says x, which is 3x minus 1, plus 1, and then divided by 3. So the 1's cancel, leaving you with 3x divided by 3. The 3's cancel, leaving us with x. So two functions are inverses of each other if essentially all of the parts of it cancel. The multiplication and the division, the addition and subtraction, they're canceling because they're undoing each other, which is why we're just left with x. That's the last thing in the problem that's not going to cancel out. Questions? So this kind of leads us into the question that I wanted to look at in your review packet. If you look at number 19, I'm sorry, the group of problems on the back of the first page there, wants you to find inverses. So this is saying find the inverse, not show that they are inverses, but we actually want to find it. And looking at number 19, 19's problem says f of x equals 4 minus x divided by 3x. So we're finding an inverse. I already have another one, and we're not proving it. We're just trying to find an inverse for this function. So the first step would be to switch x and y. So if you're finding an inverse, our goal is to flip-flop x and y. So this becomes x equals 4 minus y divided by 3 times y. There are two x's, so that means you have to have two y's in the problem. So the first direction is to switch x and y. Well, if there are multiple y's, you have to make sure you're flipping both of them. So now we have a fraction, and anytime you have a fraction, your goal should be to get it out of fraction form. How can you get this 3y so that you're no longer dividing by it?
You multiply by 3.
Yeah, we're going to multiply. So the opposite of multiplication is division. The opposite of division is multiplication. So right now we're dividing by 3y. Well, we don't want to divide by anything. You don't want to have a fraction in the problem. So get rid of it by multiplying it. So multiply by 3y. So these cancel. And on the other side, we have a 3, a y, and an x, but I'm going to write that in alphabetical order. So 3xy is equal to 4 minus y. So now there's still two y's up here, and our goal is to get this in y equals 4. After you switch x and y, you have to try and get y by itself again. So because there are two y's, and we're trying to solve for y, probably makes sense to have them together on the same side of the equation. So if there's a y on one side and a y on the other, and our goal is to get y by itself, it might make it easier if they're on the same side. So that just means take y to the other side by adding it. Our end goal is to solve for y, get y by itself. So if you look at the problem on the left, we now have 3 times x times y plus y. And our goal is to get y by itself. So thinking back to all of the different operations and types of algebra that we've done so far this year. If we have a 3xy plus a y, how can we try and get y by itself? So we have to try and pull that y out because it needs to be by itself. How can you do that? So it's a method that we would have used in chapters 4 and 5. So they have something in common. When you have two terms that have something in common, what can you do with those? That piece that's in common? Connor, what do you think? So he said divide by y because they have y in common. And instead of truly dividing by y, we're going to use it as a greatest common factor. So when things have something in common, that's called the greatest common factor. It's the first method that you would have learned in factoring back in Algebra 1 or even in pre-algebra. If they have something in common, you want to pull the piece that they have in common out. Because I want to get it by itself. So if I want to get it by itself, I can pull it out. And then Connor, if we pull it out, or I'm going to put it in quotes, divide by y, what's left on the inside?
3x plus 1.
Right, 3x plus 1. That's a type of factoring. So factoring can be done multiple ways. But when something is in common, you factor that common part out, and then whatever is left after you factor it out or divide it out goes inside the parentheses. So now y is pretty much isolated almost by itself. It just has that 3x plus 1 that is still being multiplied with. And the opposite of multiplication, Connor, is division. So if we want to get y by itself, we have to divide by whatever it's next to. Well, it's next to 3x plus 1. So we've isolated the y, we pulled it out because they both had a y in common. Now we just need to kind of make sure that it's by itself. And if it's being multiplied by anything, you have to divide by that stuff. So this cancels, you get y, I'm going to write it as an inverse. And that is equal to 4 divided by 3x plus 1. That's the type of problem that sets you apart from the other kids who are in Algebra 2. Because this is an honors level question. It's just not a regular switch x and y, subtract something to the other side, divide. This is what should set you guys apart from the regular kids in Algebra 2. Trying to think outside of the box. What else can you do to try and solve for y? Are there other questions that you have on the review worksheet? Or Deb?
Can we do 17?
Yeah. Yeah, this is a good one too. So 17, switch x and y. And then, Odette, what did you do to get y by itself? Well, one thing big. Okay, you said 17, sorry. I'm like 15 apparently. Alright, Odette, let's try again. Let's switch x and y. Alright, there we go. And then what did you do?
Divided by 4.
Yeah, divide by 4. And then
7
take the 7th root. That's it. So if you have y to the 7th, the way you get rid of the power is to take that same root. Well, it's a 7th root instead of a square root or a cube root. And then write it in inverse notation. So we have the 7th root of x divided by 4, and that's it. But whatever that power is, in order to get rid of it, you have to undo it by taking the radical, whatever that radical happens to be. So if the power is 7, we need to take the 7th root. If it was a 9, we take the 9th root. Other questions? Number 9? So number 9 wants you to take f of x and multiply it by g of x. So we have 2x squared, 3x to the 1/2 minus 5. Multiplying means, I'm going to put it in parentheses to actually show that we're multiplying a quantity. And then you're multiplying that with x, 4x to the 1/2, and then plus 1. So if you're multiplying these, we don't really use FOIL because FOIL is 2 terms times 2 terms. So instead of FOILing, what are you actually doing to multiply these? Julia?
You distribute each term to each one or the other.
Right, so this is more of a distributing problem. And you have to distribute, as she said, each term. So the 2x squared gets distributed to each term of the second parenthesis. I want to make sure I have them written correctly. So Julie, if we distribute 2x squared to the second set of parentheses, that gives us
2x to the third. And then -8x plus 2x.
So we have an x squared and an x to the 1/2. What do you do?
5 over 2.
Yeah, so you need to add the exponents. So x squared is really 4 over 2 times x to the 1/2. So you're adding those exponents. It's a little tricky because you have a whole number and a fraction you're adding together. So that would be x to the 5 halves. And then Julia, 2x squared times 1 is just
2x squared.
2x squared. So that's the first term. Then we're going to go through and do that with the next term, which is the middle term here, and that's 3x to the 1/2. And again, you have to remember that you're adding exponents. Make them into fractions. So this x to the first is x to the 1, or you could think of it as x to the 2 over 2. So Julia, you did great with the first one. So we've got 3x to the 1/2 times x to the 2 seconds, 2 over 2, so that becomes
3x to the 3 over 2.
right. So 3x, adding your exponents, a half and 2 halves make 3 halves. All right, Julia, 3x to the 1/2 minus 4x to the 1/2 is?
Minus 12x. And then just put 2.
Right, because 1/2 plus 1/2 makes 1. And then the last one, 3x to the 1/2 times 1 is just 3x to the 1/2. So there were 3 terms. We now need to distribute that last term, which is thankfully just a -5. There's not an x with it. So you're taking -5 times x. -5 and -4 is a positive 20 with an x to the 1/2, and then -5 and positive 1. So it's a pretty big problem because there's 3 terms times 3 terms, which should give you 9 terms in the end. When you're multiplying, you have 3 things times 3 things. That makes us 9 different pieces. And then trying to combine any like terms together, so keeping them in order, the largest power is 2x cubed. We have a -8x to the 5 halves, which I don't see any other 5 halves. There's a 2x squared. And then 3x to the 3 halves. And now we have some like terms. So we have a -12x and a -5x. We have the 20x to the 1/2 and the 3x to the 1/2. And then the -5. Not a lot of things combined because there weren't many like pieces, but there were those 2 pieces that had the same powers to them. Another really good problem. So kind of applying a lot of information in that one problem. So do you know exponents? Can you multiply? So that's taking like chapters 4 and 5 and then chapter 6 and kind of combining them together. So it looks like you have about 9 minutes remaining in the period, and I'll give you those 9 minutes to continue working. Remember, the answers were sent through Remind. Please check the answers on the answer key. Test tomorrow, I believe, is 60 points. It might be 65. I'm pretty sure it's 60. So this will be definitely like the largest grade. Right now, grades fluctuate so much because we have so few points. So they're going to fluctuate back and forth. But this 60 points is probably double of what we currently have right now. So please make sure you're looking just through your packet, studying tonight. Like actually look through the notes. Don't just rely on that review guide. There's definitely questions that aren't going to be on the review guide that we've covered in your packet. I can't give you questions on every single thing that we talked about in chapter 6. So go and look through your notes, kind of just peruse through them a little bit, seeing the types of problems that we've done, or look at your homework that you did. Any problems that we went over in class are probably good ones to look at as well. But yeah, because they're both the same radical, you can here, they're both the same radical, you can multiply them. So they're both the same radical, you can divide them. So what kind of graph is that? It's just an yeah. So every line has a domain negative infinity to positive infinity, no matter what. So the only time that you really have to kind of be aware of the domain is if you're dividing by x, or if you have a square root that guided. That has to be greater than or equal to 0. You're dividing by x, which does not really can't use it. I don't think you took the square root. I did. So this doesn't have an x, so you can combine these guys together. And then just get x by itself. So like back up here, you go this stuff, because that doesn't have an x, you can take this term to this side and triangle the x by itself. But I can see what you were thinking there, having those three terms, but because this doesn't have an x. No,